Good morning. In this video, we study example 2 of finding the maximum effective aperture and directivity of lambda by 2 dipole antenna. In the previous video, we discussed finding maximum effective aperture and directivity of a short dipole. Now we find it for lambda by 2 dipole antenna. Since lambda by 2 is a finite length, the antenna as compared to short dipole, the lambda by 2 dipole antenna produces a sinusoidal electric field distribution, whereas in case of short dipole it is triangular. So let's take the length of the antenna as lambda by 2. In the negative x direction, we are getting the incident wave. This is the wave incident from the minus x direction. This is the terminal resistance, and the current, peak current through the antenna is I0. Now let's compute current I at, this is y direction and this is z direction. Let's now compute the voltage for an infinitesimally small portion on this dipole dy. Since this axis is y, the small portion considered is dy. And to compute this particular voltage value, we need to replace the antenna and represent it by its equivalent Thevenin generator. So the antenna now represented as a source of voltage dV, and the resistance of the antenna is Ra. It is producing current, differential current of Di, and the terminal resistance of the antenna is RT. So this is an equivalent representation of an antenna as a Thevenin's generator. The infinitesimally small voltage dV of this generator, due to the voltage induced by the incident wave in an infinitesimal element dy, is given by dV is equal to the applied electric field E, the infinitesimally small portion we are taking dy, cos of 2 pi y by lambda. Now this term cos of 2 pi y by lambda is taken because we have taken only a small portion dy, and then we are going to integrate this equation and find out the overall voltage. So let's integrate this equation to find total induced voltage. The total induced voltage need to be found on the entire length of the antenna. The entire length of antenna is lambda by 2, and we have considered only half portion of it to find out the voltage dV, differential voltage dV. So when we integrate it, we need to consider both the sides. This is one side on which we have considered dy, and we need to take this one side and this another side. So we need to multiply the integration by 2 and take the limit. Let's consider this as a center. Since it is lambda by 2, from center we are considering this portion as lambda by 4. So for limit 0 to lambda by 4, the term E cos 2 pi y by lambda is integrated, and the result of the integration V is obtained as 2E. Since E is constant, the induced field is constant. The integration of cos 2 pi y by lambda is sine 2 pi y by lambda whole divided by 2 pi by lambda, and the limit is from 0 to lambda by 4. So the answer that we get here for this substitutions is, if you take these constant terms outside, it's 2e lambda, lambda going into the numerator, divided by 2 pi. In bracket, in place of y, since we have integrated with respect to y, we put the values of the limits in place of y, lambda by 4. If we substitute lambda by 4 here, the term sine 2 pi, in place of y, it's lambda by 4, and this is 2 pi by lambda. So lambda, lambda cancels, and 2. So it is sine pi by 2, which is 1, and sine 0 is 0. So minus 0. So the answer we get here, 2 and 2 cancels. So the answer we get for V, the induced voltage, is E lambda by pi. Now we make use of this voltage V in the equation of AEM. We have studied this equation for the maximum effective aperture in the previous derivation as voltage square divided by 4s RR, where S is the Poynting vector, RR is radiation resistance, and V is the induced voltage. So we have computed V as E lambda by pi. We have defined S in the previous derivation as induced field square divided by Z0, where Z0 is intrinsic impedance of free space, and it is defined as 120 pi. Its value is 120 pi. Now, the radiation resistance of lambda by 2 dipole is 73 ohm. Again, we are going to discuss a detailed derivation of this in unit number 5. As I mentioned in the previous video, the radiation resistance of short dipole, this is radiation resistance of lambda by 2 dipole, and its value is 73 ohms. So if we do the substitution of all these parameters in this equation, the effective aperture, maximum effective aperture for short dipole is obtained as, in place of V, I substitute this term, which is E square lambda square divided by pi square, and in the denominator there is already a term 4s. S is Poynting vector, it is E square divided by 120 pi into the radiation resistance, which is 73 ohms. So if we simplify this equation, we get 120 pi in the numerator, E square lambda square divided by 4 pi square E square into 73. So if we cancel some of the terms, pi, E square, and 120 divided by 4, so we get 120 divided by 4 as 30 divided by 73 pi into this lambda square. So 30 divided by 73 pi, we get the maximum effective aperture as 0.13 lambda square. So if you see the previous video, the maximum effective aperture of short dipole was 0.119 lambda square. That's what this was for short dipole, and now for lambda by 2 dipole antenna, the maximum effective aperture is 0.13 lambda square. So now this is a first term we have computed, maximum effective aperture. Now the second term, directivity of short dipole of lambda by 2 dipole, is given as 4 pi by lambda square into the maximum effective aperture. which can be computed as 4 pi. The effective aperture is 0.13 lambda square divided by lambda square, which comes as 1.63. So we can make a conclusion now that for an isotropic radiator, directivity is 1, and for lambda by 2 the directivity is 1.63. So the lambda by 2 dipole antenna radiates 63% more power in the given direction compared to the isotropic radiator. So this is about lambda by 2 dipole, its maximum effective aperture and its directivity. So with this we conclude that we have derived two equations: effective aperture of short dipole in the previous video and lambda by 2 dipole in this video. In the next video we will discuss the self-learning topic, which is polarization of an antenna. Thank you.